This was the introduction.
Okay, welcome people of the NCG&T seminar. Our guest this week is Jonas Schnitzer, and he's going to talk about on the quantization, dequantization correspondence for Poisson Hopf algebras. Please.
Okay, thanks first for the invitation, and thanks also to Andrea, who gave a nice introduction. So I don't have to do anything anymore, or not a lot. But just to remind you, probably. What was the big picture? I tried to. I mean, this is based on a paper with Andrea, which came out like some weeks ago, and it's a huge paper. So obviously, I can just scratch a bit. So the idea of this talk is that I mostly tell you lies, and nothing is really true. But there is a way you can make sense of it. What I'm saying, if you read the paper, it's really good. You should take a look. So, so we had this. Beautiful diagram, which Andrea was putting on his first slide, and I want to put it again on the blackboard. So we had this thing that we had the symmetric Cartier category. I think Andrea talked a lot about it, so we can assume that we have a bit of a feeling for that. But also we had some more objects in this category. Let's give this a name. B. And we had an element inside, which was what was written I co-commutative comonoid. Let's do like this. Okay. I will come back in like some minutes to write down exactly what this is. Basically, what you can imagine is that it's a co-commutative comonoid inside this category. I mean, it has a tensor product, so we know what is co-commutative, and it has some compatibility with the infinitesimal braining as well. Okay, and the second ingredient was we had a functor going from B to C, and C for me is a symmetric braided monoidal category, and it was called M-adapted. Okay, I will also come back in a second to what this exactly means. So this takes care of, so this is a M-adapted, I-braided functor. Okay, so the idea is it takes care of the braiding, the infinitesimal braiding, and has something to do with M. That's the whole, what you should keep in mind. Okay, so this is one of the parts. The next part was that we had here a braided monoidal category. And then we basically copy what was on the left-hand side. We have, let's give this also the name B, is a co-commutative comonoid. And we have a functor going from B to C, and C has the same structure as on the left-hand side, which we call M-adapted. And what Andrea... Exactly, so I cannot ask for infinitesimal. Exactly, so and basically what Andrea showed is that if I forget about this structure, so blue is probably not the best. If I forget about this structure, then this here I have a correspondence between them, okay? The correspondence was in this direction, the Drinfeld associator, and on the other direction was the Grothendieck-Teichmüller. Okay? So the point is, what does this have to do with Poisson Hopf algebras? I think there was already some hints, what Andrea put in his talk. The idea is, out of this here, you can construct, you need all these three data, like you need the category, the comonoid, and this functor. You can construct the Poisson Hopf algebra out of this. and here this Hopf algebra will be in C. Okay? And on the other side, you can construct a Hopf algebra. Okay? So the idea is quantization. I will write in a few seconds what I mean with quantization. The quantization is taking one of these and getting one of these. What the exact conditions, I mean, this is not a general Hopf algebra. We just not forget the co-Poisson structure. We do a bit more. And the idea is taking this path going up, right, and down. Okay? So Andrea showed already that we can go up by taking what we called the Drinfeld-Jetter modules. Okay? You said we have a co-Poisson Hopf algebra, we take the Drinfeld-Jetter modules, and we get one of these. To go down, actually, we also have a method. This is what I will call S with this check thing. This is for Cervera. Cervera, it's not exactly true. This is not what Cervera actually proved. This was more this thing. So what we did is basically we adapted this, the construction of Cervera, took a symmetric Cartier category and cooked up a co-Poisson Hopf algebra. And here we also have a path up, and this path up is the Jetter-Drinfeld modules, right? If you take a Hopf algebra and you take the Jetter-Drinfeld modules, you end up here. So what I need to explain you, I mean, at least what you might know is that you end up here. So I need to explain you what is these two objects in the Jetter-Drinfeld modules, and obviously on the same on this side. Okay, and then in the end, actually, this is a very fresh result. Taking these guys here and these guys, I mean, everything is a functor here. Everything is functorial. And this was, we proved actually yesterday. So, it's not in the paper, but it will be soon in the paper. Okay, and basically, quantization and dequantization is just adding the arrows to making this commutative. Like, we call this here quantization and this dequantization. Okay, so basically what I mean with quantization is go up, right, down, and then this commutes on the spot because by definition. So I will only talk about one path, but I think if you understand one path, you can do exactly the same because this is very, very mirroring. You can also start here, go up, go left, go down, and then you will have this one. I will talk about this one today, but I mean, basically it works exactly the same. Yes. Yes, exactly, exactly. And the point is, the Drinfeld associator comes always together with the specific element associated to the Drinfeld associator, this group. This group. So once you choose the Drinfeld associator, you also have the way back. So. The what? Yeah, I mean, this is. You take the symmetric Cartier category, you apply the Drinfeld associator, and it will be braided monoidal. It's not completely true, of course, because we had this funny quasi-symmetric. Yeah, exactly. So this is why I'm saying I'm lying all the time. This is basically the level of lies I will tell you. So exactly. So and here you go back, and then you will end up with this quasi-trivial Cartier. But okay. So. I mean, it's not a point. It's a series. That's exactly the point. This is exactly. This is why you need to have this H bar where you have this control that you have a notion of convergence. But in the end, in the paper, it's even a bit more general. Basically, saying that if there is a notion of convergence and the braiding is small, then you can deform it. It's going more general than the H bar thing, but this is a bit too technical to.
Is there always a trivial M that you can choose? Like if you take the monoidal unit or something, it's automatically.
I mean, the point is they really have to work together. You will see in a second what I mean with that.
Yeah, but then like as the functor, I don't know, you take the identity functor.
Yes, might be true, but then as I said, you want to go to the co-Poisson Hopf business, and in this case, the co-Poisson Hopf will be trivial. It will be the Hopf structure on the monoidal unit. There's only one, I think. Yeah. Exactly, and also the Hopf algebra itself will be the comonoidal unit in vector spaces. This is just the field, and there you have a very easy Hopf structure, namely.
Just saying that this probably always works, but it's maybe not the most exciting.
Exactly, this always works exactly, but the idea is, of course, that when I explain this in a second, then the idea is that if you go up and down, then you end up with the same co-Poisson Hopf algebra, and this will not happening with what you're saying. Yeah, but this is.
How many answers does an obvious, like, easy choice?
Yes, I mean, but it's a correct choice, but it's trivial. Okay, so the overall aim is to quantize a co-Poisson Hopf algebra. So what do I mean with that? So I take remember co-Poisson Hopf algebra, so this first four things is the Hopf algebra, forgetting the unit and the co-unit, and this is this co-Poisson bracket. And what I want to do is I want to have a quantum version of this, which is looking basically like this. You take the formal power series, and then you have maps here which are now turning this into a topologically free Hopf algebra such that the delta of x is given by the co-commutator of this quantized coproduct divided by h bar and then evaluated at h bar 0. Okay? So a Poisson structure. Exactly. And if you recall what Andrea said, that if you start with the Lie bialgebra, a co-Poisson Hopf algebra, the universal enveloping algebra is a co-Poisson Hopf algebra where you extend the Lie co-bracket as a co-Poisson structure, and then this will basically saying that this is a quantized enveloping algebra for the Lie bialgebra. So if I succeed this, then you see immediately that we can quantize Lie bialgebras on the spot, because Lie bialgebras are basically an example of these guys here. This Andrea knows better probably, so he nods. I think it's correct.
So you could take a Lie bialgebra with underlying Lie algebra, a complex C-simple one, then the quantization to the right would give something isomorphic to the Grünfeld Jimbo of the H-bar version.
Okay, so keep this in mind. This is probably I will leave it even on the blackboard. This is the path we are going to take. This is the aim we want to get. Okay, so let's go to the second part, which I call adapted functors. Okay, this is actually, I should call it a bit different, because the first definition, I think I do not define what is a co-commutative comonoid. I think this is clear. So for a symmetric Cartier, and M is a co-commutative comonoid, then it is called I co-commutative if mean, I didn't write that, of course I have a coproduct here. So co-commutative says it's compatible with the braiding, right? So, I mean, I can write it down here. This means if I apply the braiding after the coproduct, I get the coproduct back. And infinitesimally co-commutative means it is a co-commutative one plus the infinitesimal braiding kills the coproduct. Okay. So what one sees is that if we have this in a braided monoidal category, a co-commutative comonoid, then we can look at what Andrea did. So braided monoidal category B, we apply the Grothendieck-Teichmüller, and what I'm claiming is then that M in the category which Andrea denoted like this. This was this funny Grothendieck-Teichmüller element, making it into a symmetric Carté category. Then this is I co-commutative. Okay? So why is that so? I mean, recall that how you define the new associativity and the new braid, the braid relations was basically just series, whatever coefficients, we don't care, but the series were given by the old braiding squared. We put it at somewhere, but if you have this here, I mean, it stays for sure co-commutative. What was the infinitesimal braiding? It was the logarithm of the braiding square. The logarithm of the braiding square kills the coproduct, because the logarithm of the braiding square is a series in identity minus the braiding square, right? With some coefficients I can never remember.
So just to recall, so on the level of objects, the category C, G0 is just
it's the same. The morphisms are also the same. You just change the associator and the braiding, exactly. Exactly, yeah. This was the log of sigma square, right? The braiding. And this, as I said, this is a series in identity, something like this with some coefficients, which you can look in Wikipedia. I don't remember how the logarithm is defined. But anyway, so it's a series in identity minus the square, and this kills definitely this object here. Okay? So, first bullet point. The second one, if this, I take now a symmetric Carté category, and this is infinitesimally co-commutative, then this guy is co-commutative. Same argument, the associator was changed only in series of the infinitesimal braiding, and the braiding was also only changed with an exponential of the infinitesimal braiding. So since this infinitesimal braiding will kill this guy, only the first orders of the series will contribute, and the first orders were given by units. Same argument is really something you can easily compute. Exactly. So what we have now is, we know what is these two objects, and in fact now we showed, I claim that somebody showed that you can take even this guy here and do the same here, right? So we can include these guys, and we have, if we have an object here, we get an object here, and the other way around as well. Okay.
This level here is not yet an equivalence, right? It's just weird functors or maybe
I mean, it's actually an equivalence. I just want to hide it a bit.
on this level, okay.
Yeah.
But it was not shown by you. This is what the work.
It's implicitly written in Chevera already. I mean, I think in this specific statement that this is an equivalence of categories. Also, I didn't talk about what is the morphisms on this side, right? I mean, this is not, I mean, you should think of the category of symmetric Cartier categories with all these properties, and then actually the morphisms are a bit more involved than you think. I mean, they include also this guy and the functor, but in the end, everything will be an equivalence of categories. Okay, so we take a co-Poisson Hopf. Okay, then we've seen in Andreas' talk that we can choose the category B to be the Drinfeld-Jetta module over this guy. This is an infinitesimally braided monoidal category, or symmetric Cartier. This is, sorry, it's the same objects. And we can and here I need to look because this is a bit more involved, but also just that I mean, I don't hide too much. It's just so it's a bit a longish formula, but it's not important how this formula exactly looks like. But what I'm saying is that you get this funny Lico action Andrea defined. The left action is just a multiplication, and the C minus is just C itself as a vector space. Okay? And what I'm claiming is that this is an co-commutative comonoid with, I mean, there's one thing we didn't use yet. This is the coproduct here. So we use the coproduct. And the co-unit is just the co-unit of the underlying Hopf algebra. This is the coproduct of the underlying Hopf algebra. So what you need to check is that this guy is actually a morphism of Drinfeld-Jetta modules, right? I mean, but you can check that, and you have to believe me that this is true. Exactly, of the Werner module on the Jetta-Drinfeld part. This is actually the next example. Is if you take a Hopf algebra, then what you can do is you can define the category to be the Jetta-Drinfeld modules over the Hopf algebra. Okay? And in the same way you do, how is it? You define the left action of the Hopf algebra by the multiplication, and the right action again by I don't want to spell it out. It's not the coproduct. There is something more complicated.
So here we take the adjoint coaction.
Yes, exactly. And this one here, as I said, here we didn't use the coproduct because we used this funny formula, but we have the coproduct left. So this guy turns it into a co-commutative comonoid. Okay, so we have on both sides, we have an example. And in fact, if you look at this, taking Drinfeld-Jetter modules or Jetter-Drinfeld modules, we didn't even produce only the category, but we also produced the comonoid on both sides. You mean the plus one?
So you could take the adjoint action and as a coaction just take the co-product.
Exactly.
Which I guess in the co-Poisson
This
thing would then correspond to you change the product somehow using the...
Exactly. There is this exact opposite thing. There is on every, I mean, I wrote here a minus for a reason. There is also the plus option. The plus option will give you, you don't start with a co-Poisson Hopf algebra, but with a Poisson Hopf algebra. Because you need to have the bracket here, right? If you change the ideas of this guy. Anyway, believe me, that the plus one will not end up in the Drinfeld-Jetter modules of a co-Poisson, but there is something very similar, which is called the Drinfeld-Jetter module of a Poisson Hopf algebra. And this would correspond to, basically it's just dualizing everything. It's really, really dualizing everything. So if you take a co-Poisson Hopf algebra, then the dual should be a Poisson Hopf algebra. And here, if you dualize, you change the roles of co-product or co-action and action, and you will get exactly like what you said. And here you do the same, but then you see that you will get the Poisson action instead of the Poisson co-action. Yes.
There are two ratings.
There are two monoidal structures.
One structures, so if the difference minus you consider one and plus you consider the other one.
Exactly.
You take the product with one where the action is like the diagonal one and the other one is the up one?
Exactly, yeah. And it's really crucial because only for one of these two monoidal structures, this guy is actually a morphism of Jetter-Drinfeld modules. Yeah, both does, for the braiding you don't care because this is just, you need to check that it's a morphism in the category. You don't apply any braiding. So you need to be a bit careful. There is one monoidal structures on the Jetter-Drinfeld such that this guy is actually a morphism of Jetter-Drinfeld modules. And this is the one where you take the op coproduct or something like this. Is it correct? I don't remember which one. Okay. So as I said, coming from here, we have already two of the things we need. So let's define what is a adapted functor. So what we have is that this is either a braided monoidal or a Cartier, a symmetric Cartier, sorry. And we have a if we are in this case, we have a co-commutative comonoid. If we're in this case, we have an I-co-commutative comonoid. And then we say, oh now, okay, I changed, let's do like this, it's better. So we have a functor from a braided monoidal symmetric Cartier category into C, and this is for me now a symmetric braided. Huh? Ah yeah, M is in B. Exactly. And I can see this in two ways. I can see this as a symmetric Cartier category with trivial infinitesimal braiding. So if I choose infinitesimal braiding to be 0, all the compatibilities are canonically, or I see this just as a braided monoidal category. Okay? There are two ways, and depending on in which situation I am, I choose the correct one here. So it's Cartier with t equals 0, or it is braided monoidal by forgetting that it's symmetric. Okay, and then this is a bit the aim of the talk. I write down two equations, but in the end we will not care anymore. It's just that it's not that difficult. So is called M-adapted if you have two morphisms you can associate to, you can more, but I always need to check the stuff. And of course, I didn't introduce the epsilon. Epsilon is the co-unit of M. I apply the functor, and then I have the zero part of the comonoidal functor. I forgot here, yeah, comonoidal. This is the F0 part of the comonoidal functor. So this is a morphism going from from the monoidal unit in C and F of M. And the second morphism, I will not even write it down, I just tell you how to get it. So there's a morphism which basically goes from, what can you do here? You can apply the coproduct. Okay? And then you can use the F2 basically to get the morphism going from going in here. Sorry, this is M tensor Y. Okay? So this is the morphism gamma xy. It's applying the coproduct and then splitting the tensors off. And it's called M-adapted if this both are isomorphisms. Okay? There is actually a nicer way to phrase that. So this will not be super important, but if you have a co-commutative comonoid, tensoring with it is a comonoidal functor. So what these two equations say is that if you go from B to B, tensoring with the fixed element and then applying F, that this is a strongly monoidal functor. So that the splitting here is an isomorphism. Okay? This is a bit more compact way to say it, but you need to, basically you need to check that this is a comonoidal functor, but it's not that hard. Okay, so this is basically what I will do next, yeah. This is basically what I will do next. And the thing is, we make just, as we did here, some funny side remarks. So if you have M in C, I co-commutative comonoid, then and you have an adapted functor. Then we've seen that what Andrea said is that this applying the Drinfeld associator is functorial. So we got a new functor. I mean, it's written here with the index of the Drinfeld associator, but actually this functor doesn't change. It's defined the same on objects and the same on morphisms. But the interesting thing is M adapted. And for that we need to remember what I wrote here. If you apply the Drinfeld associator and you have an I co-commutative comonoid, it will be a co-commutative comonoid, so we know what is M adapted in the setting of braided monoidal categories. Okay? Then basically same statement. If this is a co-commutative comonoid and F is M adapted, then this guy here is M adapted. Okay? This you basically see that the conditions what you have here, they don't, I mean, they will not change in the end because M, you really don't do anything. Okay? And I mean, you can just check by hand that the conditions are still fulfilled for this, and the functor doesn't change as well, right? So, I mean, you have to be a bit careful because I obviously removed all the associators here, but you apply associators, but anyway, the associators only change in order h bar, so if you have an isomorphism in order h bar 0, then you can build up high isomorphism. Okay, so once again, we can look in the middle. And what we've seen is now we enlarge this to this guy, to this here. Right, so we included all of this. But now what is missing, if I follow the paradigm of what I did on the left-hand side, I should tell you if I go from here to here, what is the adapted functors I can build here. And this is, let me check if yes, this is the examples, what I do. So, examples. So, I mean, I didn't provide a lot of examples for this category, so let's stick with this. We take the Drinfeld Jetta of a co-Poisson Hopf algebra. We take the infinitesimally co-commutative comonoid which we defined here. And now the functor, in this case, again, I'm cheating a bit, going from C and let's say vector spaces. Okay? And what I'm doing is I take the co-kernel of the multiplication, and so this is a map from C tensor V to V, and I'm taking this co-kernel, and this is basically what Thomas said. This is taking this co-invariance. Is it called like this? It's a co-kernel, so. Okay. I think it's called co-invariance, right? Okay, so it's I mean, of course, this is a bit everything put under the carpet, but this is the whole idea of this talk. So this is, you can make it into a comonoidal functor by splitting this off in the co-kernels of a tensor product and I mean, it's really, there's an obvious choice. The only thing what implicitly you should keep in mind is that I assumed here that my Poisson Hopf algebra is in vector spaces. So if I want to perform this thing, I need a notion of co-kernel. So I need to assume that my category has co-kernels. Obviously here, vector spaces have co-kernels, so this will be a bit important later when we go to formal power series because they don't have. But just keep in mind, and what you can check, this guy is C minus adapted. Okay? So we have all the ingredients together. And in the second case, so we take the Jeter-Drinfeld modules of a Hopf algebra. Then we had this adjoint or coadjoint, I always forget which is the correct word, comonoid, and we can take the vector space, again the functor in the vector space, and actually it looks, let's give it a different name at least, that to pretend that it's something else. But in the end, it's exactly the same what you can do here, because here a Jeter-Drinfeld module also has a co-action, an action, and you take the co-invariance with respect to the action here. So what you're doing is f of m mu m delta m goes to, or is the co-kernel of mu m minus co-unit identity, and this goes now from H tensor m to m. Okay, it's exactly the same. We don't even need to change anything. We don't even have to pretend that it's something else. It's exactly the same. And this is in fact H minus adapted. Okay? I mean, in fact, you can check that in both cases, just for your convenience, what is the easiest to check is that this guy here, or this curly f, this is isomorphic to the forgetful. And actually, the same. Okay, this is really easy to check because you know how the product works. I mean, this really, there's no secret behind that.
Like this should be the fundamental theorem of modules, right? This is saying you tensorize with one Hopf algebra, you build the co-invariance, and this gives you back the same thing we started with.
Andrea, you know that? I have no idea. I don't know what is a Hopf algebra.
This is why all the time I say to you, the Wells construction is exactly what you just said.
Okay. So now, obviously, I removed exactly the part I would like to point at now. So here, if you remember, there was Poisson Hopf algebras, and we had this thing going up. But now we have all the ingredients up, right? We have exactly symmetric Cartier category. We have the comonoid, or the infinitesimally co-commutative comonoid, and we have this guy here. And the same here. Here was Poisson, and here actually is the structure up here. Okay. In fact, what I said in the very beginning, this is actually functorial. Like, starting with the Hopf algebra, you can construct this category, and if you have a morphism of Hopf algebras, you can get a functor plus the special properties with the special stuff here connected. So this is actually functorial. Okay, so now what I want to take care is this is also a bit sketchy, but what I want to do is, we didn't talk about how to come from here down, okay? If I have this, how to get a co-Poisson Hopf algebra, and on this side, if I go down, how to get a Hopf algebra. So the next part is, I mean, I always give this mathematical terms even though I don't do anything. So I call it construction of co-Poisson Hopf algebras. And I will basically just start with a theorem. And this theorem is originally from Cervera, and then probably, Cervera proved it, so how to get a Hopf algebra out of this setting, and what we did is we showed how to get a co-Poisson Hopf algebra out of this setting, but compared to what Cervera did, this is very little, so I would say that I write the names here very little, just to give credits to the correct people, because really Cervera did all the work and we checked the compatibilities or how to get the co-Poisson structure on the left hand side. Okay, and the theorem says, so actually two theorems again. So let C be a braided monoidal category. And, braided it, yeah, good. A braided monoidal category or a symmetric Cartier. Then, and F, oh God, I always mix up the F is an M-adapted functor. And obviously M is either a co-commutative comonoid or an I-co-commutative comonoid, depends on which situation you are. But then I will make it very quick and not enlightening at all. Then this is now an object in C, okay, is or can be endowed with the structure of a okay, so you take this guy here. So if you have a comonoid, then also the tensor product is a comonoid. Then you take, so the coproduct on this guy is given by f of the coproduct of this guy, and there are formulas for the rest. So the antipode involves the braiding. I don't want to write down the formulas because in the end, who cares, right? The only thing what we need again is, I call this the probably Rivezzi approach, is that we don't care about stuff, we just need properties of the stuff. And in fact, there is something which is a very nice property of the stuff, is let's check what it does, what we have already, right? I didn't tell you anything, how this looks like, so you have to believe me everything what I'm saying, but we have the infinitesimal co-commutative comonoid, and we have an adapted functor. And the same for in the Hopf setting. So what we can see is actually something very nice. and this is, I kind of make it short, so f of C minus, the C minus was the Drinfeld-Jeter module associated to co-Poisson Hopf algebra, and the co-Poisson Hopf algebra was C. So now this theorem tells me that this guy is a co-Poisson Hopf algebra. So does anyone have a guess? What is it? And we only have one, right? So this is C. The same thing, I had this curly f. This is not a minus, sorry. This is the Hopf algebra H. Okay? So we had this thing that exactly, we had the co-commutative comonoid, we had this adapted functor, which you believed me that it is an adapted functor. So this guy is a Hopf algebra, and in fact it's just isomorphic to H itself. Okay. So I have a bit minutes left, right? So I will try to give at least a hint. So just to come back here, what we had is co-Poisson Hopf algebras, and we are now very, very comfortable in moving up and down. We take a co-Poisson Hopf algebra, we find this category. On the same, we have a Hopf algebra, and we can find this object, and we can also go down using this theorem by Cervera. And the idea is now to combine now in the last few minutes going up and down and going left and right. Okay. So this is now a bit wishy-washy, like exactly the opposite to what I did before. So let's start with a co-Poisson Hopf algebra and let it be topologically free. And what I mean with this is I want to have that this is the formal power series over a vector space. I want to have a product, a coproduct exactly like this, plus what I want to have is that this guy here starts in order h bar. Okay? So how, for example, do you get it? Take a co-Poisson Hopf algebra in vect, then extend every morphism here h bar linear, and then scale the co-Poisson co-bracket with an h bar. This would be one example how to get that. Okay, then we can, oh, that's the wrong one. Then we define this category. This is now a Drinfeld-Jeter. So what I put a bit under the carpet, this is a Drinfeld-Jeter module in the category of topologically free modules. So this is a topologically free module, and these are maps also having higher orders than h bar. But what I'm claiming, or what I want from them, is that this should be a V probably, that this V is also of this form. So this co-Poisson co-action, or how you want to call it, also starts in order h bar. And why do I do that? This is now a bit tying in with what Andrea said. So basically what you can check, first of all, you have that this guy is inside here. You can check that by the formula I wrote down many minutes ago. basically what you have to check is that the minus delta is starting in h bar, but it contained one copy of this guy, and this one starts in h bar, so it will also stay in h bar. Okay, then what you're doing is you can check that this is infinitesimally braided. I mean, I didn't tell you, but I take the full subcategory where objects look like this, but with infinitesimal braiding, being like this, okay? Because the infinitesimal braiding, what Andrea wrote down, always contained at least one of these deltas. They start in h bar, so the braiding has to start in h bar. Very easy. Okay. So now we think back to Andrea's talk. Sorry, and probably I should mention that I restrict this functor here we defined before, taking the co-invariance, I restrict to the subcategory, and all of my objects are in the subcategory, so this still stays adapted, right? I mean, the conditions were for every object, we just take fewer objects, so it stays adapted. And here I'm pretty much lying because actually this doesn't end up in this category, because taking co-invariance for a formal power series, you might create something which is not topologically free anymore. But let's forget this. Just remind that if you want to make a computation, which will never happen with this, then then you should take care of it. And okay, so we think of this guy, and then what we're doing is we're using the theorem of Andrea, saying, okay, or the theorem we discussed in the beginning, we apply a Drinfeld associator, which we can now, because the infinitesimal braiding is starting in h bar, we get an adapted functor here, and we end up here, okay? And then we use the theorem of Cervera, because this is now C minus adapted.
Why don't you deform the target category?
Because basically this I see as a category, as I said before, with infinitesimal braiding equal to 0. And if I take infinitesimal braiding equal to 0, the series will, this is the same as this one. Because there is no infinitesimal braiding. Exactly, so now Cervera tells you that this guy here is a Hopf algebra. In topologically free modules. Okay, and in fact, even though the functor doesn't actually end up here, if we add one element being this module here, or in this sense it's this one here, then it's isomorphic to the forgetful one, so here we definitely get a topologically free one. And what we get is that this is a quantization of this. Now is a Poisson Hopf algebra, right? And now you see exactly, if you look at this diagram and you put in the stuff I deleted, you see exactly what I did. I went with the Poisson Hopf algebra, I attached the symmetric Cartier category, Then I realized I cannot apply the theorem by Andrea, so I restricted the category in order to enforce basically that it's quasi-trivial. Then I applied the theorem by Andrea. I ended up here. And here to go down, I used Cevera. And with the Cevera, I get the quantization of a Poisson Hopf algebra. So this is the whole idea. Understanding up and down, combining with left and right. And what you get is a quantization. So just a few remarks before I stop. Is obviously, I decided to go the quantization direction, but you could also do the opposite because this is very, very similar. You can start here, go up, define a similar subcategory, and go here, and then go down. So what you get is, you start with a Hopf algebra and get a dequantized one. And in fact, you can do, so first of all, this is functorial. And as I said, in this diagram, everything was functorial, so we're just composing functors, which is still functorial. Then you can do the same for dequantization. And dequantization obviously is also functorial. And the next thing is Q and dq, this was dequantization, quantization, are actually inverse functors. Okay, so I didn't provide all details, but what I told you is that there is a category of Poisson Hopf algebras and a category of Hopf algebras which are categorically equivalent via quantization and dequantization. You have to keep in mind that there should be some h bars involved, so the Hopf algebra should be commutative up to h bar, and then there is really a one-to-one correspondence. And another thing is, I will keep it short, I say, the representations of a Poisson Hopf are isomorphic. It's not true, but I write it to the representations of the Hopf algebra you quantize. So basically, it's not really isomorphic, but we saw that the Jetter-Drinfeld modules, the Drinfeld-Jetter modules on this side, doing some stuff that it fits in the framework of Andrea, you can put on this side, and actually you can ask now, using the Drinfeld associator, you can ask now, what is this category? We know it's a braided monoidal category, but actually you can check that this is the Jetter-Drinfeld module of the correspondent quantized Hopf algebra. Okay? So basically I could also write here that the Drinfeld-Jetter of C, I can apply the Drinfeld associator, and this is isomorphic to Jetter-Drinfeld of Q of C. Okay, this is what I mean with the representations are isomorphic. On objects, it's the same basically, you just change associativity and the braiding. Okay, but I think I stop here. I'm already 5 minutes over time.
Thank you, Jonas, for this nice talk. Are there some questions?
So, I mean, particularly for the last point, if your category is abelian as well,
Yes.
and you can talk about the growth and decroup,
Yes.
what happens to the growth and decroup under the quantization?
I have no idea. We have an evening to find out.
I mean, the question is motivated where if you go back to the Drinfeld-Jimbo quantum groups and the quantization process that Andrea guarantees us is actually an example, then for that category, well, yeah, you're not looking at your Drinfeld modules anymore, you're looking at modules. Okay, so my question is a bit confused, actually.
I didn't realize.
Okay, I'll pass the questions.
I mean, maybe I have a follow-up question that might be close to what you might have in mind. I don't know. So I quite like the part where you start with the Hopf algebra and you go up to the braided monoidal category.
Yeah.
With this M and this functor that you basically M being H and you just view it as a commutative as a
Co-commutative
comonoid in the category of Vieta-Drinfeld modules. Yeah?
Yes.
So let's say your Hopf algebra has some more structure. Let's say it is a quasi-triangular Hopf algebra. Then there's another braided category that you can attach to it, and that's just the modules. So you take the R matrix, this gives you the braiding.
Yes.
And you look at modules, and then this is a braided monoidal category. And I'm not sure, but I think if you look at the transmutation of the Hopf algebra, you should be able to understand this as a co-commutative, actually Hopf algebra, in the category of modules, which is now a braided monoidal category.
Might be, yeah.
So this seems to be
The first
another functor that goes from the right lower corner to the right upper corner.
But I mean, the idea is, I mean, here you also need this one here.
Yeah,
I think on the modules it's not completely clear what it is.
Yeah, I'm thinking. So maybe for the modules, what should it be? Like if you take, so okay, B should be the modules of the Hopf algebra, which is braided because we take the R matrix, and then C, is it just vector spaces? I mean, is it just the forgetful functor, maybe?
Then I mean, I think it will not be adapted. I think. I mean, in case, I mean, in the end, you don't care what is here.
I care a lot what is here. I don't know.
No, but what I'm telling you is you should not care what is there. I mean, what precisely is inside there? If you can attach, I mean, it's not only that we attach the braided monoidal category and a comonoid and a functor. We also attach the data such that we can reconstruct the Hopf algebra.
True.
This is a bit more than just saying we attach this stuff to
Absolutely.
this.
So in this case with the R matrix, I think this will be via Tanaka-Krein. So
But don't you get the double with Tanaka-Krein? No?
No.
Then it might be the same, yeah. Or it might be similar working.
Like a different functor, but of course this needs more structure because
I
you
mean,
need the R matrix, otherwise this is not working. Yeah.
Once you have a category from which is braided monoidal, and you can reconstruct the Hopf algebra out of it, you can search for this part here, because I think the modules, they should somehow include this co-Poisson, whatever this exactly is.
This I don't understand, but this would like be co-Poisson in a braided sense.
Exactly,
yeah? So
exactly. Probably in an infinitesimally braided sense, and I think there is some parts in a paper by Chevera who's talking about this. So there are formulas which say what is infinitesimally braided Poisson. And then if you have the same thing, like if you have Tanaka-Krein here, then you can reconstruct the Hopf algebra, and you would have something like a co-Poisson version of Tanaka-Krein, and you can reconstruct the Hopf algebra, then there is no problem, you can do the same. I mean, I'm providing one example going from Hopf algebras to braided monoidal categories, and then we have this very old theorems saying that we can go back and forth, like between infinitesimally braided or symmetric Cartier and braided monoidal.
So
but the way you arrive here actually is not that important.
So, but yeah, this could possibly be another class of examples that fit nicely into this picture.
Yeah, sure. I mean, this is actually, I think I asked you already if there is something on this side, like Tanaka Klein or something like this.
This I do not know. Okay, do we have more questions? Oh.
Hi, this is Jan. Can you hear me?
If this Grothendieck-Teichmuller group acts on the space of Drinfeld associators, that means then that you have an action of this group on the Poisson Hopf algebra. As in, like, you look at the quantization. So for every, you see.
Yeah, I think so. Yeah. I'm not sure exactly what this tells you, but I mean, of course, there is more structure which we didn't use yet. Yeah.
Because you're fixing the.
Exactly, because we are fixing. I mean, implicitly we fix one Drinfeld associator, which fixes us this curve of Grothendieck-Teichmuller and.
Yeah.
But in fact, I mean, we didn't check what happens if we, because now the input is exactly one Drinfeld associator, but we could put another one.
Yeah, exactly. Yeah.
And then we would have, like, because this acts transitively, we would have a Grothendieck-Teichmuller element going from one to the other, and this probably, as you said, acts on Poisson Hopf algebras. Yeah.
So you've got like you're a family of quantizations parameterized by this Grothendieck-Teichmuller group.
I think so. Yeah.
What the hell does it look like in some simple examples? This not simple examples. I mean, I guess there's just one.
I mean, there is. I think that now this comes out of the blue. I never understood how this works, but it is conjectured. That it's the Galois group of the of the algebraic closure of the rationals. Yeah, it's conjectured that it is that. I think Drinfeld even conjectured that. I think the Grothendieck-Teichmuller group, yeah. So, and there are people working on approaching this conjecture, yeah. But yes.
Maybe that's a good place to stop. No?
Okay, so let's thank Jonas again. Thank you. And see you next week.
Can you hear me? Hi.
Sorry, so if there are some questions, Jonas is still here. You can ask him. So just unmute yourself and go for it.
Can you hear me?
No. Wait a second.
Hello.
Okay, just 1 second. We fix the audio and then.
Hello.
Ah, yeah.
Can you hear now?
Yes.
Now we can hear you. Yeah.
Hi. This is Jan. Thank you for tonight's talk. I have a few comments. One of them is about this about quasi-triangle Hopf algebras.
Perfect.
What Thomas was asking. So Drinfeld-Dieter modules. This is the same as normal, just algebra modules for the double of the Drinfeld double of the origin of the Hopf algebra H. So I think this is a connection between the two stories. And if you have a normal Hopf algebra without an R matrix, you can consider its Drinfeld double, which is an R matrix. And modules for this will be Drinfeld-Dieter modules.
This is true, but like here, I'm asking something slightly different, right? So I'm saying, so what happens if you take any R matrix on H, not on the Drinfeld double? And because then you could also look at the corresponding modules, and they would form your braided monoidal category.
Yeah. So I would be surprised if one finds an adapted functor.
I don't know. I was just saying that I think I recall that that in this case the transmutation should give you a co-commutative Hopf algebra even in the braided monoidal category of the modules. So at least M is there, but of course you still need the functor. And okay, here the guess would be you take the forgetful functor, but one has to check if this works. Probably not. Yeah.
No, it will not be.
No, the forgetful
functor will not be.
Okay,
then
then
you need to. Yeah, the functor needs to something like remove half of the dimension or something like this.
Okay, so right. So here we need again some invariance or co-invariance. Okay.
So what Raymond was asking, so this is true that there is Grothendieck-Teichmuller acting on the space of all quantizations. Yeah. And it's not easy to make this action explicit. There is work by Kiselev, who is, I think, doing a slightly similar, or maybe somewhat related, but I'm not sure if this is Grothendieck-Teichmuller, but he is acting by some diagrams on quantizations of Poisson manifolds. But it looks like you do a lot of work to compute action of one diagram. Okay, thank you.
Okay, thanks for the question. Do you have some comment, Miriam, or?
One small comment was that so if the category of modules over the Hopf algebra is graded, then it embeds into the category of Yetter-Drinfeld modules. But then I don't know what is obtained from that category.
Okay, then let's thank Jonas a third time, and let's see you next week.